Hello and welcome back to another Physical Sciences 3 lecture. So, we are looking at radioactive half-life today, and we'll have a look at this graph because it's quite a nice graph, really. If we have at the start here, we're starting off with 1 or 100% of our radioactive substance. Okay, after one half-life, see here, we've got one half-life down here. We are now at 50% of the radioactive um, like the radioactive emissions. So here, so half-life, the average length of time it takes for half the parent nuclei in a given sample to decay is called the half-life of the radioactive isotope. So after one half-life has elapsed for a given isotope, not only will there be only half the number of that type of nuclei remaining, but the activity or rate of emission will have decreased to half its original value, usually measured in becquerels. The half-life does not indicate which nucleus will decay, but rather it indicates the statistical chances of decay. Right. So it can be quite confusing to people. So, and the notion of decay can be quite confusing as well. So, I just want to make a few notes here. That if we're given a sample, then the mass cannot be created or destroyed. So, if you have like a rock of some sort of sample, uranium, then it'll decay to, after one half-life, we can say that half the rock is uranium and half the rock is X, where X is the decay product. Okay, so if you measured the mass, so therefore if you measure, and I'll try and spell measure correctly, measure the mass of that sample, then the mass will still be the same. And that's because our, say, uranium has just decayed. It's decayed, so half of this rock would now be uranium, um, but half of it will be just another type of element, whatever the uranium has decayed to. Okay, so that's often an exam question or something like that. So they say why they measured the mass after their decay and why are they surprised that the mass is the same. It's because it's just decayed to another element. Half-lives vary from fractions of seconds to billions of years. Okay, so depending on the element, um, it will have different half-lives. For example, coffee has a half-life of I can't remember now. It's about 10 hours or something like that, and that means that it'll leave your body during that time. So something bismuth or bromine or something like that, um, like lower half-lives may be useful in medical equipment or something like that. So if you're making someone ingest it, you don't want it to be staying in their body forever. But something like carbon is useful for radioactive dating, and we'll talk about that in a minute as well. Our example, radioactive dating. Okay, so we can tell how old something can be because things have a certain amount of carbon when they're living in them, and so depending on how much carbon-14 has decayed since they died, then they can tell how old something is. But that also has restrictions based on the fact that after so many times, so many half-lives, there's just negligible carbon-14 anyway. So it has a restriction or has a limit on how old it can measure things to be. Okay, so consider strontium 90, a beta emitter with a half-life of 28 years. And if we had a strontium with mass 100 milligrams, having activity of 3200 becquerels, then 28 times the amount of strontium would only be 50 milligrams, and the activity would have dropped to 16 becquerels. So let's say this was so that's the amount of strontium left in the sample, but the sample would still weigh 100 milligrams. Let's say it was pure strontium to start off with. 50 milligrams would be some other element. Okay, and then so on and so. So after another 28 years, 50% of the 50 milligrams and 16, so it's just halved again to 25 milligrams and 800 becquerels. And after another 28 years, we would expect 12.5 milligrams of strontium and 400 becquerels. Okay, so note the decrease in mass of strontium-90 is accounted for in terms of the new mass of the K product, which is yttrium-90. So strontium-90 turns into yttrium-90. So the red dots here represent the strontium, and the rest of this sample is made up of the green dots, which is the yttrium-90 here. Okay. So, example. An ancient wooden artifact contains 5.6 grams of carbon-14. Given that the artifact is 28,650 years old, and carbon-14 has a half-life of 5,730 years, how much carbon-14 did it contain when new? Okay, so first of all we need to know how many half-lives there are. Half-lives have passed. And we're just going to divide is equal to 28,650 divided by 5,730, and that's equal to 5 half-lives. Okay, so to work out how much it started off with, so then how much C14 did it contain when new? When new contained 5.6 times 2 to the power of 5, which is equal to 5.6 times 2 to the power of 5, is equal to 179.2 grams. Okay, that's exactly the same as getting in our calculator and just saying 5.6 times 2, and then times 2. So that's 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives. So you can do it that way as well. You can say 5.6 goes to, what was it, something like 11. I'll try and get this up on my other screen so I can keep it. So it goes to 11.2, and then that goes to 22.4, and that goes to 44.8, and that goes up to 89.6, and then that goes to 179.2. So you can do it either way. You can either do it the mathematical way, like that, or you can show it just like each step, like that. And you can reverse it the other way. So if they said 179.2 grams was present at the start, and now there's 5.6 grams, then you could actually just reverse this process and say 179 divided by 2 is 89.6, divided by 2 is 44.8, divided by 22, divided by 2 is 22.4, divided by 2 is 11.2, divided by 2 is 5.6. Then you say, therefore, there were five half-lives in that process. So there'll be different examples that way, and it's totally fine to show your workings out either way as well. Some cases it will be better to actually show it this way, and in other cases it will be better to show it this way. So just practice lots of those half-life examples. Hopefully the concept's not too difficult for you. It's just a matter of how long does it take for half of the radioactive material to decay. That's all a half-life is. Okay, we'll see you next time.